So let's continue looking at acids and bases, and what we're going to look at now is sort of how do we define acids and bases in terms of this hydronium or this hydroxide concentration. In this chapter, honestly, we are focusing on aqueous solutions of acids and bases. In the last chapter, we talked about Bronsted-Lowry, we talked about Lewis, we talked about Arrhenius definitions, but really here we are concentrating on aqueous solutions, and so we're looking at mostly Bronsted-Lowry or an Arrhenius definition, though Lewis also applies, but we're focusing on aqueous. So if we think about how we would look at different kinds of solutions, let's compare it to pure water. So in pure water, we know we've got the same concentration of hydronium ion and hydroxide ion. We know that at 25 degrees Celsius, that concentration is 1.0 times 10 to the negative 7th. And so that's essentially how we define what a neutral solution is. A truly neutral solution would be a solution that, even though it might not be pure water, has the same concentration of hydroxide and hydronium ion concentration. We would then define an acidic solution as something that has more hydronium ion than it has hydroxide ion. And so what that means for us at 25 degrees Celsius, so let's remember these values for hydronium and hydroxide that we calculated in the last section, these are true at 25 degrees Celsius. And so acidic solution would be something that has a concentration of hydronium ion that is greater than 1.0 times 10 to the negative 7th. And so we saw an example of that. If we had 0.20 molar solution of hydrochloric acid, that gave us a hydronium ion concentration of 0.20 molar because the autoionization of water really didn't end up adding anything to that hydronium ion concentration. A basic solution, therefore, is going to be defined as one that has less than 1.0 times 10 to the negative 7th at 25 degrees Celsius. But really, truly, our definition is that the hydronium ion concentration is less than the hydroxide ion concentration. And so if we have a 0.050 molar solution of sodium hydroxide, that would give us a hydronium ion concentration of 2.0 times 10 to the negative 13th. These values that include a calculated amount, so this 1.0 times 10 to the negative 7th, these are the ones that are only true at 25 degrees Celsius. These definitions that we have in parentheses here, these are true no matter what. Okay, it's just we don't have a specific number to compare to unless we're doing it at some particular temperature. And so powers of 10 can be a little bit tricky to think about, especially when we're talking about things that are very small. So 10 to the negative 7th is a really small number in my brain. 10 to the negative 14th, also a really small number. And I don't have a great sense of the difference in those two very small numbers. And so something that we do to help us deal with those very small powers of 10 is we define what we call the pH. So this notation of a lowercase p in front of a value is essentially negative log of whatever that thing happens to be. And so when we define a pH, what we're talking about is the negative log of the hydronium ion concentration, or we will shorthand it as the negative log of H plus concentration. So if we look at our examples here, we had our 0.2 molar solution of HCl. That ended up being a 0.20 molar solution of hydronium ion. And so the pH of that solution is just going to be the negative log of 0.20, which gives us 0.70. So acidic solutions have low pHs. If we look at our other example, if we look at 0.50 molar so that we can keep 2 sig figs in our concentration of the sodium hydroxide, in the sodium hydroxide concentration and the hydronium ion concentration, we get a hydronium ion concentration of 2.0 times 10 to the negative 13th. And so our pH there is going to be 12.70. Now you might be thinking, these sig figs look really strange. And that's because when you take a log, the significant figures rule is a little bit odd. Believe it or not, these are given to the correct number of significant figures. And so the way that significant figures work when you have a log is that the result of a log actually has two parts. The numbers that come before the decimal place are called the characteristic, and what they tell us about primarily is the power of 10 of that number. And so in this case, that 12 is really just giving us information about the power of 10. The 0.70, or the things after the decimal point, are what are referred to as the mantissa, and the mantissa is the part that actually has the information about the value. And so this is actually the only part of that pH that's significant. And so the fact that we have two numbers after the decimal place and two numbers in our concentration is actually the correct way to deal with that number of significant figures. And so basically the rule, if you're looking at pHs or other kinds of things, POH, pKa, that we're going to talk about later, is that the number of decimal places, or the number of places after the decimal point in your pH, needs to correspond to the number of significant figures in your molarity of whatever it is that you're talking about, or in the equilibrium constant, because we'll see some pKa's and things like that later. And so that's what you're looking for. So this is actually properly done, even though it looks a little weird. It's really 2 sig figs going to 2 sig figs. Okay, so let's add that column to our definitions here. So neutral, acidic, basic, we have our definitions in terms of how the ions relate to each other. So hydronium ion is equal to hydroxide for a neutral solution, hydronium is greater than hydroxide for acidic, and hydronium is less than hydroxide for a basic solution. If we're doing this at 25 degrees Celsius, we have actual number to compare those things to, because that's our neutral. And what that means then is that our pH scale has something to compare to also. And again, this is just at 25 degrees Celsius. The scale is a little bit different if you're doing this at a different temperature. But at 25 degrees Celsius, the dividing line in pH between acidic and neutral is 7. And so something that's acidic is going to be generally between 0 and 7 on the pH scale. Technically, you can get into negative numbers, but most of the time we won't see that here. And for basic solutions, you're going to go from 7 to 14. Again, technically you can get a little higher than 14, but we really won't see that in this class much. Things get a little complicated at pHs higher than that. So if we look at some examples just of things that have different pHs that might be familiar, milk is actually a little bit on the acidic side. So milk has a pH of 6.4. Your blood is a little bit on the basic side. You have a buffer in your blood that keeps that a little bit basic. Other things that are probably fairly familiar, carbonated water or any carbonated beverage like the Diet Coke that I'm drinking right now has a pH that's in the range of around 3.9, around 4. And so those are acidic. That's why your dentist doesn't really want you drinking them, because it's not great for your teeth, all that acid. But it's part of what makes them taste good. Lemon juice is pretty acidic, and that's from the citric acid that is in any kind of citrus fruit. Vinegar is basically acetic acid, so depending on the concentration of the vinegar, you have sort of a range of pHs there. And your stomach acid, hopefully that's not surprising, is pretty acidic. So depending on exactly how acidic your stomach acid is, it could be anywhere from a pH of 1 to 3. You'll notice hydrochloric acid, if we have 1 molar hydrochloric acid, if we calculate the pH for that, that's 0. So that's kind of our end of the scale that we're going to talk about here. If we go to the other end of the scale, we'd be talking about 1 molar sodium hydroxide, or any strong base for that matter. 1 molar strong base, we're going to have a pH of 14. So we're going to look at another thing that we can define that allows us to do some calculations sort of very quickly. And so again, this P notation here simply means negative log. Okay, so if we're talking about the POH, probably you can guess we're talking about the negative log of the OH minus concentration. So if we start with our Kw expression, again, Kw is going to be hydroxide ion times hydronium ion concentration. If we're at 25 degrees Celsius, that's 1.0 times 10 to the negative 14th. And so let's assume we're going to do this at 25 degrees Celsius. Honestly, a lot of the problems we're going to do in the rest of this chapter, that's a safe assumption, but I'm going to continue to reiterate it just so you don't forget that a lot of these things that we're doing are depending on that Kw at 25 degrees Celsius. So if we take the log of both sides of this equation, we're going to have the log of hydronium times the log of hydroxide, or hydroxide times hydronium. On the left-hand side, we're going to have the log of that Kw on the right-hand side, which is 1.0 times 10 to the negative 14th. If we do that log, what we get is negative 14.00. And again, remember, these digits after the decimal point are the ones that correspond to the significant figures in our value. And so 14.00 is the correct number of sig figs, even though it looks a little bit strange. On the left-hand side, we've got we have the multiplication of two values inside of the argument of the log. That's the same thing as the addition of the logs of the two values. And so we've sort of split that up into two logs. And one of them should look pretty familiar. This is pretty related to the pH. This one is fairly related to the POH that we're going to define in a second, but with one major difference, and there's no negative sign in front of either one. So we're going to multiply this negative through. We're going to get negative log of OH minus log of H plus will give us 14. Now we literally just have the pH here, and we have what we're going to define as the POH as well. So the POH, again, is just defined as the negative log of the OH minus, and so we get what looks like a fairly simple equation. So the POH plus the pH is going to give us 14.00. I will remind you, however, that 14.00, that is dependent on that kW at 25 degrees Celsius. We can write a slightly more generic version of the equation, where instead of it being 14, it's the pKW. And so again, this P is just the negative log of the thing we're talking about, which in this case is kW. So if you have something at a temperature other than 25 degrees Celsius, you could calculate this pKW and use a similar expression. It just won't be equal to 14. And so you'll have a slightly different value that you'd be working with there. Okay, that one is good at any temperature. As long as we know what that kW value is, we can use it. So let's assume we're working at 25 degrees Celsius. We know our POH plus our pH is going to be 14, which means our pH is going to be 14.00 minus whatever the POH is. And this can actually simplify certain calculations for us. In some situations, say if we're working with a strong base or something, it might be most convenient to have the OH minus concentration instead of calculating the H plus concentration directly. And so we can use this as sort of a shortcut to get from the POH to the pH sort of quickly through that OH minus concentration. But again, you can only use this version of the equation at 25 degrees Celsius. So for example, if we go back to our 0.050 molar NaOH solution at 25 degrees Celsius, we've already calculated the pH through the H plus concentration. But if we do this from the OH minus perspective, it's a pretty straightforward and quick calculation. So the hydroxide concentration is 0.050, which means that if we take the negative log of that, we get the POH. And again, sig figs here makes sense. We've got 2 sig figs in the concentration. We're going to get 2 after the decimal place in the POH. Plug that into our pH, and we're going to have 14.00 minus 1.30, which gives us the exact same pH that we got by going through the kW and calculating it that way. And so it's a really convenient shorthand, but again, please remember, it has to be at 25 degrees Celsius if you're going to use this value of 14.00. Okay, one other thing to talk about with this pH is if we have a pH, we can from there calculate the hydronium ion concentration. And so pH is defined as the negative log of the H plus concentration. Let's multiply our negative over, and then let's take the opposite of the log, the anti-log. And so what we would get then is that our H plus concentration is going to be 10 to the negative whatever the pH is. So for example, if we wanted to know what the hydronium ion concentration was for a solution with a pH of 9.20, we would basically take that 9.20, put that into the power with a negative sign in front of it. We have 10 to the negative 9.20. Now pHs are the result of a log, so the only part of it that's significant is this value that's after the decimal place. So even though this looks like 3 significant figures, it's really only 2 significant figures in that pH. And so that's all we can report in our hydronium ion concentration. It would be 6.3 times 10 to the negative 10 molar for that particular solution.